When we look at the vast expanse of the universe, filled with its planets, stars, and galaxies, a fundamental question arises. Why is there something rather than nothing? This mystery deepens when we consider the delicate balance of the laws of physics that govern the universe. These laws treat matter and antimatter similarly, yet when we observe the universe, we find that it is predominantly made of matter, with antimatter being scarcely present. This imbalance raises questions about the forces that shape the universe, leading to the cosmos we observe today, with its galaxies, stars, and the ongoing mystery of our own existence. For centuries, scientists believed that the universe was timeless and eternal, governed by unchanging physical laws. However, in 1927, Belgian priest and scientist Georges Lemaitre proposed a different idea. He suggested that the universe began as a single, dense primordial atom that exploded, giving rise to the smaller atoms we see today. Lemaitre's theory initially garnered little attention, but in 1929, astronomer Edwin Hubble discovered that the universe is not static. It is expanding. This revelation led some scientists to propose that if we could rewind the universe's history, it would eventually shrink back to an incredibly small, dense point. This theory, humorously dubbed the Big Bang by astronomer Fred Hoyle, was later embraced by many. Despite early skepticism in the 1960s, astronomers Arno Penzias and Robert Wilson accidentally discovered cosmic microwave background radiation, the lingering heat from the Big Bang, while attempting to tune into microwave signals from the Milky Way. This accidental discovery provided significant evidence for the Big Bang theory. If the Big Bang theory is correct, how did it lead to the formation of stars, planets, and galaxies? Through careful calculations and observations from telescopes and space missions, we now have a clearer understanding of how the universe unfolded. About 13.8 billion years ago, all matter in the universe emerged from an incredibly hot and dense point in a violent explosion. The universe expanded at an astonishing rate, doubling in size every 10 to the power of -34 seconds, creating space as it rapidly grew. During this brief moment, fundamental forces such as gravity took shape, and energy transformed into particles of matter and antimatter, most of which annihilated each other. Fortunately, some matter survived, leading to the creation of protons and neutrons within the first second. These particles began to fuse, forming the first atomic nuclei of hydrogen and helium. Around 300,000 years later, atoms formed as electrons combined with these nuclei, filling the universe with clouds of hydrogen and helium gas. Roughly 380,000 years after the Big Bang, the universe left behind a faint glow, the cosmic microwave background radiation, which Penzias and Wilson had detected. Within this radiation were tiny fluctuations in matter, stretched across vast scales during expansion. These fluctuations would eventually serve as the seeds for the formation of galaxies and cosmic structures. Today, as we examine the vastness of the universe, our detailed observations, despite inherent uncertainties, consistently point to a coherent story. Our universe consists of matter and adheres to the universal laws of physics. It operates under the framework of general relativity, expanding, cooling, and evolving with elements influenced by dark energy, dark matter, ordinary matter, neutrinos, and radiation. Within this universe we find a tapestry of galaxies, stars, planets, heavy elements, and, in one corner at least, intelligent life. These vast structures did not exist from the outset but emerged over time through a process of cosmic evolution, an extraordinary achievement of scientific reasoning realized in the 20th century. Through detailed calculations, scientists have reconstructed a timeline showing how the universe transitioned from a nearly uniform state, made mostly of hydrogen and helium, to the complex and diverse cosmos we observe today. As we trace the origins of each structure and component, we face the question: how did each individual element come to be? Delving further into the origins of existence, we reach a fundamental inquiry. Can everything we see have emerged from nothing? Life, as we know it, arises from microscopic particles that make up the fabric of our reality. These particles combine to form complex molecules, the building blocks of life. However, molecules did not appear ex nihilo at the universe's inception but evolved through a prolonged process within the grand cosmic show of stellar life cycles. Stars are born, live out their divine lives, and eventually die, triggering the formation of new materials through cataclysmic events. These materials, in turn, fuel the birth of new generations of stars, sustaining the cosmic cycle. This intricate exchange nurtures the conditions necessary for the formation of planets and the complex chemistry that supports life. For the universe to exist in its present form, certain pivotal events had to occur. Gravity guided the formation of galaxies and cosmic structures, requiring an initial mass that gravity could condense into larger formations. Dark matter played a crucial role in preventing the dispersion of matter during the early stages of cosmic evolution. Additionally, a delicate balance of various types of matter and radiation was essential for the creation of cosmic relics like the cosmic microwave background radiation and the chemical components of galaxies. Integral to this story is the mystery of matter and antimatter. In the early universe, matter and antimatter should have existed in equal measure, but our universe is overwhelmingly composed of matter. Various theories attempt to explain this discrepancy, including scenarios where physical laws temporarily distorted, creating conditions favorable for matter generation. One such idea involves the concept of spallation interactions within the standard model of particle physics. As we ponder the origins of our universe, we confront a significant mystery. Did the universe truly emerge from nothing? While uncertainties remain, our ongoing quest for understanding continues to unravel the complex tapestry of cosmic evolution, pushing the boundaries of our comprehension and questioning the very nature of existence. The universe begins with these profound questions, challenging our grasp of reality despite its elusive nature, plays a crucial role in how we interpret the universe. While it cannot be composed of the particles described in the standard model of physics, various theories explore its origins. Some suggest that dark matter could have emerged during the early hot phase of the universe, surviving through subsequent cosmic epochs, while others propose that it arose during the universe's expansion and cooling. Alternative hypotheses consider it to be a unique type of neutrino or even a product of gravity, giving rise to exceptionally heavy particles. This leads to a pressing question. Why does dark matter exist today when the early universe seemingly functioned without it? The origin of dark matter involves complex energy dynamics, leading to intriguing discussions about its source. One captivating possibility arises from the theory of cosmic inflation, which proposes that prior to the hot Big Bang, the universe underwent a rapid expansion driven by incredibly high energy density inherent to space itself. As this expansion slowed, it catalyzed the creation of matter, antimatter, and radiation, giving way to the universe's subsequent evolution. Notably, inflation predicts specific density fluctuations that align with observations, lending significant support to its validity. However, while inflation offers a framework for understanding the universe's birth, it also raises philosophical questions. Can we truly comprehend a state without space, time, and the laws of physics? From a philosophical standpoint, we might define nothingness as the absence of these fundamental elements, but from a scientific perspective, defining nothingness becomes a complex task. Scientifically, it's challenging to describe the absence of something, as there's no framework for understanding a void without space-time or the physical laws that govern it. While some theories suggest the universe may have arisen from nothingness, they also highlight the limitations of our understanding. The quest to unravel the mysteries of existence stretches the boundaries of human knowledge and perception. Quantum theory opens up fascinating possibilities regarding the nature of fields and particles, challenging conventional ideas about time, space-time, and physical laws. Some theoretical frameworks even propose that the universe could have originated from nothing, rooted in quantum theory. This idea revolves around the notion that quantum fluctuations could spontaneously create a universe. Despite the lack of definitive mathematical proof, this idea remains speculative. Recent advancements by physicist Don and his team from the Wuhan Institute of Physics and Mathematics have made significant strides by providing the first mathematical evidence that the Big Bang could have resulted from quantum fluctuations. Their work draws on key principles, including the Wheeler-DeWitt equation and Heisenberg's uncertainty principle. The Wheeler-DeWitt equation, a cornerstone of quantum gravity, combines quantum mechanics with general relativity but does so without involving time. Meanwhile, Heisenberg's uncertainty principle explains the transient nature of particles in a vacuum, where particles briefly emerge from and disappear into nothingness due to random quantum fluctuations. By combining these principles, Don's team demonstrated that a minuscule vacuum bubble could rapidly expand, potentially triggering a Big Bang-like event. This novel approach also suggests a connection between dark energy and quantum potential, inspired by the pilot wave theory, a lesser-known interpretation of quantum mechanics. The universe hypothesis presents an alternative to the traditional Big Bang model, proposing that our universe may have emerged from a collision between two higher-dimensional brains within a larger, hidden reality. This collision would release energy and matter, igniting the creation and evolution of our observable universe. While still speculative, these ideas challenge our current understanding of the universe's origins and encourage exploration of new avenues of inquiry. The Eric universe hypothesis offers a fascinating departure from the prevailing inflationary model, suggesting that the event that birthed our universe may not have been a one-time occurrence but rather part of an ongoing series of collisions and evolutions. Each cycle could potentially create a new universe, leading to an eternally expanding cosmic landscape. Within this framework, other theories abound regarding the nature of our universe. It could be the result of a grand experiment conducted by an advanced civilization in a higher dimension, designed to explore the mysteries of life and fundamental forces. Alternatively, our universe might be a projection emanating from a higher dimensional domain, hinting at the possibility of a holographic existence. Some even entertain the idea of the universe as a conscious entity undergoing a journey of self-discovery through its worlds, stars, and living beings. As we grapple with these profound concepts, it's essential to acknowledge the limitations of our current understanding of the universe. While the Big Bang remains a pivotal event in cosmic history, it may not mark the definitive beginning of all existence. The early stages of cosmic evolution reveal a universe teeming with possibilities for life to emerge, driven by enduring principles and materials that govern it. Despite the role of randomness in shaping our universe, the emergence of life underscores the inherent potential within the vast fabric of existence. It is now our responsibility to embrace and explore this potential, striving to unlock the secrets of the universe and define our place within it.